let's look at just a computational example. Suppose that we have a group of students and their mean weight is 140 pounds with a standard deviation of 30 pounds. What fraction of the students weigh between 90 and 190 pounds? All right. How do we get traction on this? Well, we need to see whether we can express that range from 90 to 190 as the mean plus or minus some number of standard deviations. Right, we want to express that range as mean plus or minus some standard deviations, and then we know that the fraction, what is Chebychev's inequality is going to tell us something about the fraction that can be more than a certain number of standard deviations away from the mean. It's going to say that that can't be very big, and so what's that going to tell us about the fraction of numbers that are within that number of standard deviations? It can't be too small. Right? So you're not losing very much when you go far away. So you have to have quite a few of the observations in the middle. All right. So 140. If 140 is the mean, what's the range 90 to 190? To get from 140 down to 90 is subtracting 50. Yes. To get from 140 up to 190 is adding 50. So that is a symmetrical range around the mean. It's the mean plus or minus something. And we want to express that something as a multiple of the standard deviation. Okay, if the standard deviation is 30 pounds, then 50 is how many 30s? 1 2/3 30s, right? So the range plus or minus 50 is plus or minus 1 2/3 standard deviations. Is that okay? All right. So the fraction of numbers in the list that are above 190 or below 90, the fraction that are k or more standard deviations from the mean, is at most 1 over k squared, where k is 1 2/3, right? We're looking at, so the fraction that's outside is no bigger than this ratio, which is 36%. So what can we say about the fraction that's within the range 90 to 190? Yeah, it's at least 100% minus that, right? So it's at least 64%.